Capacitors are common in electronic circuits. Have you ever wondered, what do capacitors do in a circuit? Welcome to video 9 in our series, Basic Electronics Using Fusion. In this video, we'll look at the three main uses of capacitors in circuits. Capacitors perform three functions in a circuit. 1. They can smooth out voltage fluctuation on sources. 2. They can block DC present on a signal, leaving only the AC portion. And 3. They can filter our AC signals, giving us the frequencies that we want. Let's look at each use. Rarely do electronic circuits draw current from their sources in a smooth manner. Most often they switch on and off quickly, or change their current draw at a rate demanded by input or output signals. This circuit is an RC oscillator which produces a square wave pulse output. If we simulate it in Fusion, we can see the voltage at the capacitor and at the output. We'll also see the current from the power source. Our simulation results show the current fluctuations present in the power source, V1. Current rises and falls depending on whether the output is high or low. Here's a simple rectifier circuit that converts AC to pulsating DC. And looking at the simulation in Fusion, we can see that the load receives a positive pulsing wave, but it's not very smooth. Adding a capacitor will smooth the output of these circuits. Here's the effect of adding 10 microfarads of capacitance. During the quarter cycle of the input, the capacitor charges. Then, as the input voltage decreases, the capacitor discharges and supplies power to the load. And the cycle repeats, charging and discharging. Similarly, we can simulate switching noise on a 5-volt supply with the following circuit. When we simulate the circuit, we can see some high-frequency noise riding on top of some lower-frequency noise. If we place a capacitor across the supply rail, as shown in the circuit, we'll see the higher frequency noise diminishes dramatically. Switching loads can also cause supply rails to sag. This circuit switches in a 100 ohm load every millisecond. The 1 ohm resistance represents the resistance present in the wiring. When simulating the circuit, we can see the supply drops 5 millivolts each time the 100 ohm is switched into the circuit. And zoomed in, we can clearly see the drop lasts the duration of the pulse time that the 100 ohms is switched into the circuit. Now, if we place a capacitor across the supply rail feeding the load, we can see that the supply rail drops less. Zooming in on a pulse reveals why. During the time the 100 ohm load is switched into the circuit, the capacitor discharges slowly through the load, preventing the supply rail from sagging as much as it did without the capacitor. Capacitors also block DC. In the circuit above, the amplifier IC2 will amplify the input signal 45 times. The input signal is the output of microphone MK1, which contains a small signal riding on top of a DC value. When someone speaks in front of the microphone, a varying signal on top of the DC value will be produced. We only want to amplify the varying signal and not the 4.5 volts that it's riding on. So C1 blocks the DC, and only the AC part of the signal is fed to the amplifier. C1 is also said to couple the signal from the microphone to the amplifier, and DC blocking caps are often called coupling capacitors. The third common function of capacitors are their use in filter circuits. This circuit simulates an optical sensor used to measure a heartbeat. The sensor is placed across a finger. If we look at the Vout op-amp signal, we can see that the output of the amplifier contains a lot of noise. But the filter circuit made up of resistors and capacitors will filter out the unwanted frequencies, leaving our heartbeat signal. To recap, we've seen how capacitors can smooth out voltage fluctuations on sources. The capacitor bypasses the effect a switch load has on a power supply rail. This capacitor is often called a bypass cap for that reason. It's also said that the capacitor decouples the effect the switched load has on the power supply rail, and for this reason some people call it a decoupling cap. We've also seen how caps can block DC in a signal and pass only the AC portion of a signal. Because the capacitor couples over the AC signal to other parts of a circuit, this cap is often called a coupling cap. Lastly, we showed how capacitors combined with resistors can filter out signals, giving us the frequencies that we want. There are more applications for capacitors, but we'll save those for a later time. In our next video, we'll look at capacitor units of measure and construction.